Good afternoon. Thank you for coming again. It is the fourth time that I'm speaking in this room about cell nucleus, and today I will be mostly speaking about dynamics of the nucleus. To begin with, I'll tell you a few things about repetition. We discussed repetition before, and I told you that repetition is led by the end of the chain, and the repetition is prohibited when you have things which have no ends, such as rings. But repetition is controlled by this parameter, an entanglement, which was invented by the founders of modern polymer physics. And this is a miracle, as I was trying to explain to you, because the very concept of entanglement is quite delicate. Entanglement in elementary lectures is supposed to be illustrated by operating fingers like this, which suggests that it's a two-body, two pieces of chain phenomenon, while in fact it is not. So how it works is sort of a miracle to some extent, but the fact of the matter is that all sorts of crumpled globules, all models of crumpled globules with fractal dimension larger than 2, they exist when chain length is longer than this entanglement length, when entanglements are important. If the system wants to be unentangled, then it avoids entanglement starting from this magic length and entanglement, which is why it's an important parameter not only for material science, where it shows the crossover frequency between elastic behavior and viscous behavior, but it is also important for things like chromatin, where it shows the crossover from something more mundane to something more crumpled with higher fractal dimension. So here I just, as a joke, assembled many pictures taken over years in various places in Paris, showing entanglements of various kinds. And I particularly like this lion, which entangles its paws in peculiar way. And also, what else? This snake, of course, also did something weird. But anyway, speaking about entanglement lengths. Entanglement lengths, there is a very sophisticated way to estimate entanglement length, knowing basically only the density of your polymer mass. This is a formula which was derived by Everayers and company in this paper here, quite a number of years now ago. It involves density measured in the number of Kuhn segments per unit volume and Kuhn segment cube. So it's sort of volume fraction on the level of Kuhn segments. So here are all the estimates for this quantity. And this volume fraction is about 20 for chromatin. And this is normal thing for regular polymer material, nothing unusual, this number. And so if you go through all this arithmetic, you discover that depending on what you assume about density, how many nucleosomes are there, and depending on how big is your nucleus, you obtain estimates for this entanglement length anywhere from few kilobase pairs to a megabase pair. So it's quite sensitive. Where this crumpled globule regime begins, it's quite sensitive. In a very recent paper here in 2023, people reanalyze this question using the same Everayers formula they analyze this question in the light of what people know about loop extrusion and things like this. So the claim is that what loop extrusion does is it basically transforms the fiber into a sort of a bottle brush polymer. And since these loops are assumed to be basically probably shorter than entanglement lengths, so they themselves do not create extra topological constraints. And therefore, this polymer is shorter and thicker. And it actually changes quite dramatically the value of entanglement length. It sort of fluidizes the whole material. If you view nucleus or interface nucleus as just a material, so this makes it more fluid-like and less elastic-like. So this is how reputation idea plays out in this context of chromatin. And now I want to switch gears and tell you about macroscopic flow. So I told you it becomes a little more fluid. So how does it flow? Now I want to completely switch gears. I want to forget the fact that this chromatin fiber is a polymer, and just consider contents of nucleus is a field, as a continuous material, and this material somehow flows, and I want to know how it flows. Of course, it flows both because there are thermal fluctuations and because there are active processes abound, so we will have to consider it. But before, let's review in a few slides what is known about experimental situation in terms of this type of hydrodynamic flows in the nucleus, nucleus-wide. So the most complete experiment of this type was performed about 10 years ago by my faculty colleague Alexandra Zidovska when she was a postdoc, and it was based on this so-called displacement correlation spectroscopy when people label some of the histones, specifically H2B, but it doesn't matter too much in my eyes. And then they were making essentially photographs of the whole nucleus and making them with short times interval delta t. They were able to identify which labeled spot moved where. And this way, they were able to construct, first of all, of course, they can look at the dynamics of every particular labeled point. And this dynamics is indicated here is subdiffusive dynamics, which we discussed. I showed you this picture from the earlier paper. It's a subdiffusion. And we discussed that it may be similar to Rao's model or dissimilar to Rao's model. And there is no complete satisfactory explanation. But qualitatively, we understand that it's sort of a subdiffusion of some kind. But complete theoretical real explanation is missing here. So what kind of subdiffusion is there, we do not quite know. But in any case, it's subdiffusion. But now, since they have many of such points, they can actually construct hugely informative maps. So these maps, each picture represents the whole nucleus. And what is color-coded there is the direction of velocity vector. Okay, so if you have something yellow, that means velocity vector in the observation time was pointing, let's say, I don't remember which color is what, but let's say yellow means velocity upward, and blue means velocity downward, and green velocity left and right, and so on. So what you see is that basically, and this, by the way, represents very similar figure from the same Alexandra a few years later. I'm not entirely sure what is the difference between these two, so it's basically the same idea. So what happens is for a few seconds, you see that there is large domain of yellow. This large domain of yellow means that whole piece was moving in a certain direction, the whole piece, like this. While some other piece, for instance, blue, was moving maybe upwards in some other direction. So the point of this picture is to see that there are sort of big domains which move coherently in agreement with each other. They move as solid pieces. So the first thing that I want to emphasize in this connection is that these pieces are not territories. I told you that in another type of labeling, if you label every chromosome, then different chromosomes occupy different territories. So I was very inviting to think that, oh, this is another demonstration of the territories. One territory moves this way, another territory moves that way. So if you imagine that these territories are like geographical map of some country, some, I don't know, French departments. Pieces of France are called departments, is that true? Am I right? Okay, so different departments, and now you imagine that different departments move coherently, whole department moves somewhere. I don't know if that analogy explains anything, but... Sorry? Sorry?
What are the two big holes in the nucleus of the upper slide?
Those are nucleoli. Here is nucleolus, and here is nucleolus, and these nucleoli somehow persist. They don't move on that scale. Why there are no nucleoli here, I don't know. Yes?
So these velocities depend on the time scale at which you look at them?
Yes.
So the longer you look at them, the more consistent.
Yes, yes, because at short time scale, they don't form yet. And at longer time scale, they die away and they start to dissolve. So here they are less consistent than here. So on a longer time scale, they start to dissolve. So this is a puzzle. Why is that? And an additional piece of this puzzle is indicated right here. When ATP is depleted, or somehow ATP hydrolysis is suppressed by some biochemical means, all this beauty disappears, and of course you still observe some fluctuations, but these fluctuations have nothing, have no correlated, coherent nature. They are very random. Yes?
At first, there's no domain moving in the same direction. Do you think there's a bias or a bias of imaging or a phase transition happening at a certain time scale where there's domain moving in the same direction?
I don't think there is. I don't expect to see any phase transition there. I just see it. I think that what happens is when it's observation time. This delta t is not how long the system moves. The system moves all the time. It's observation time. If you observe for a very short time, then they don't. Each labeled unit does not move very far, and therefore when you average these small displacements, you don't see very much. In order to see, you have to observe for some time. Just imagine a group of people, and they move, of course, they don't move strictly like this. They move somewhat randomly, but on small time scale, their random relative motion dominates. And only when you observe for sufficiently long time, then you see this coherence. Okay, so.
Why does the nucleolide disappear if you take out ATP?
Sorry?
Why does the nucleolide disappear if you take out ATP?
That's a good question, and
True on the picture as well.
yeah, I must admit I don't know. I don't know. It may, I don't know.
It seems smaller.
Hmm?
They seem to separate into smaller ones.
Yeah, maybe. In fact, the function of nucleolus is very much ATP dependent. But why they seem to disappear, or I don't know. The answer is not known to me.
So is it a projection, a 3D projection onto the...
It is a slice.
It's in the slice.
It is a slice. Okay. So how can we understand it? We should consider that there is each unit, of course, has two forces, and this is quite trivial formula. And we basically know what to do if the system is thermally driven, then there is fluctuation dissipation theorem. If the system is active, then something else happens. And how do we address that? So the way to think about it, I think, is to resort to something that polymer physicists knew for quite some time from this paper by Doi and Danuki, that you can think of this polymer system with solvent as a two-fluid object in which solvent, in this case nucleoplasm, flows and polymer flows too. So then you have polymer velocity, which which is different in different places, and this is exactly what was color-coded by Alexandra measurements. And there is solvent velocity, and there is, of course, volume fraction of your polymer, which is potentially maybe different in different places. So then you write down standard, it's hydrodynamics. Now you exercise what you know about hydrodynamics. You have force balance. So those are forces acting on the polymer. You have friction force when polymer moves past solvent or other way around. There is, of course, viscous stress. There is osmotic pressure of this polymer, which the gradient of osmotic pressure you can also treat as gradient of chemical potential of this polymer. So this describes sort of the diffusional flow of the polymer if it has higher concentration in some places. And then there is hydrostatic pressure, and this is the same story for the solvent. So, okay, this is good. So what happens is we means Robin Brunschmann, Itzhak Rabin, Alexandra, and myself, we analyzed that question, and we wrote this equation, and we said that this stress can potentially have active component. There are active processes, right? And osmotic pressure can potentially also have active component. So how do we think about it? Active stress, you should think about some force dipoles. It must be force dipoles and not force monopoles because of something that Archimedes told us. Archimedes told us that if you want to move the Earth, you have to find the place to stand on. Okay, which means you have to have force dipole. You cannot apply force monopole to the planet. You have to have another planet to apply second force. So another formulation of it is, of course, the third Newton's law. So this is force dipole. And this is a very schematic drawing by my own hand. How do you imagine force dipole? You imagine some protein which perhaps grabs two pieces of DNA and pulls them closer or pushes them apart, something like this. Okay, so then it's a and yeah, by the way, I forgot to say that we call this vector sources, and we also call scalar sources. Because of some chemical transformation, this piece may become better solvent, worse solvent, something like this. It contributes to osmotic pressure. Okay, so we...
Sorry, what is VS and VP?
Sorry?
What is VP and VS?
VP and VS are right here.
Yeah, what is it?
Oh, it's polymer velocity and solvent velocity. So this is friction force. This is the same equation that I wrote here.
How can you measure it?
How can I measure it? Yes, it's an excellent question. Polymer velocity you can measure if you label some monomers. For instance, if you have histone H to B, which is presumably attached most of the time, you measure polymer velocity. If you want to measure solvent velocity, as far as I know, nobody was able to do it so far. But of course, you have to place some reporter particles which do not attach to the polymer, and then you measure solvent velocity. And at the end of the day, I will tell you that some of the predictions are very much related to it. So it's an interesting question if it is possible to measure within some reasonable amount of effort. Although I learned many years ago that irresponsible theorists like myself should keep mouths shut offering experimentalists to do experiment, because for a theorist it costs nothing, and for an experiment it may be very difficult. But in any case, it's in principle measurable quantity. Okay, so we went through, I will not go through all this mathematics. We went through all of this, and we discovered, not surprisingly, that longitudinal flow fluctuations are controlled by these scalar sources, the sources that change locally solvent quality, while transverse flow fluctuations are controlled by vector sources. And as a result of it, we found through some mathematical treatment of all these equations, we found something that is, that depending on, there is some functional form of this measured quantity. She calls it FSD. What is the FSD? It's fluctuation spectrum density, I guess, something like this. And it has peculiar functional dependence on this delay time delta t, which is reasonably accurately reproduced in these experiments. So it's all okay. But more interesting is something that is not in our theory, but it is observed in experiment when you look at it from this point of view. When you consider the spectrum density as a function of wave vector, you discover that both ATP depleted systems and native systems, they have the same pattern of fluctuations at large Q. At small distances, it's the same fluctuations. And notice that not only they are similar, but quite significant details of the spectrum are reproduced without ATP. They, even little peaks here and so on, all of them are the same. At the same time, the small Q behavior in the system with ATP is very, very different. You have much more of fluctuations. And this is exactly what was said at the beginning, that if you deplete ATP, then all these coherent motions is something that happens at small wave vector, they disappear. So that's just more, sort of more mathematical, more scientific statement of the same fact. So if you look deeper into this, you discover something interesting, something that gives great pleasure to a theorist, but also gives a big pause. What you discover is that, in fact, if you want to observe coherent motions, which means if you want to observe a parallel motion of different pieces, then through this mathematics tells you that your force dipoles must have nematic order. Your force dipoles must be parallel to one another. On qualitative level, this is very appealing, very trivial, because if they are randomly oriented, well, their efforts sort of average out and they do not push the system anywhere. It is only if they are parallel, then they have collective effect. And what happens is, at this level of description, it's entirely puzzling. What could be the reason why they would be parallel? In normal, I use the word nematic because just to say that they are parallel. But in normal nematic material, molecules are parallel because they are elongated molecules, and they prefer to be sitting parallel to one another like this. It's easy. But these motors, whatever they are, they do not sit too close in the nucleus to form nematic for the reason that they touch each other by their elbows. They are not packed like passengers in New York subway in the rush hour. They are relatively far dispersed, and therefore it is entirely puzzling. Sort of this result translates one puzzle into another puzzle. From the first puzzle, why material in the nucleus moves in coherent blocks. It translates in another puzzle. Why are these force dipoles parallel? It's not any easier. So in some sense, this paper, although referees of Biophysical Journal gave positive review, but 10 years later, I give them a reason to reject this paper, because this paper did not prove anything, did not do anything despite all effort. So what's going on? The problem remained for a few years completely open until this simulation by Mike Shelley and company was performed. And in this simulation, they found something super exciting. You see, for instance, here, they observe dramatic, perfect, beautiful nematic order of polymer itself. Not only of motors, but of polymer itself. Beautifully, beautifully ordered. something that was entirely missing in our analytic theory. So, of course, the question is, what did they assume in their simulation? When you analyze it, you see that basically their model is not any different than our analytic model. They did the same thing, except we wrote some equations on a piece of paper, and they realized the same equations in computer. So what could be the problem? One problem is that they did not include hydrodynamic screening. They neglected hydrodynamic screening. I will explain the nature of hydrodynamic screening in the next slide, but there is a second point which turns out to be even more interesting. Look at this picture. This explains their model. And you see there is force dipole. There is this monomer and force F. I don't see this. Is it A? It's probably A. FA in this direction and minus FA in this direction. So initially, when you see it, you think it's very, very similar to the drawing which I presented to you here. One force and another force, FA and minus FA. Okay, so it seems very, very similar idea. But if you think about it in the model, in their model, these two forces are applied. It looks like they are applied at neighboring monomers. And the monomers are connected by a rigid bond. So if you apply two forces on a rigid bond, unless, of course, you apply force which is too strong and you break the bond, nothing happens, right? So when I was speaking about it, I got excited and I decided to demonstrate it on this piece. So I said, if I apply force like this, nothing happens. But of course, I applied force in the wrong way and I disassembled my pointer. So, but indeed, the idea that if you just literally do it like this picture suggests, nothing happens. These forces have no effect whatsoever. So what they did is they did something super clever. I do not know if they realized how clever was their idea, but it was super. So the idea was that computationally they apply one force, exert one force on the monomer, and another force on the solvent in the place where second monomer is supposed to be. And that is the key idea. So let's discuss these 2 points one by one. So first, it's just simple. Forget about nucleus, everything. I'll tell you what is hydrodynamic screening. So imagine that you have a cloud of this, I will call them monomers, but you can imagine that this is, by the way, you can imagine that this is a view from above of some forest. So this is trees, and there is, in the field outside of the forest, there is wind. So there is a flow of liquid in this direction. And here, the flow is almost insignificant. You do not see it. You do not feel it. So how far, how deep it penetrates into the flow, into the set of obstacles. In order to find it out, you can balance forces. So the flow here moves because it is entrained, it is pushed, pulled, moved by this liquid here. So this corresponds to a gradient of velocity, v divided by this distance lambda times viscosity. That is the force which pushes. And it's balanced by the friction force against all these obstacles. The number of obstacles is concentration times this depth, and this is friction for one obstacle. And if you solve this lambda, you find that the penetration depth goes like concentration of these obstacles to the power minus 1/2. With, to make units work correctly, this should be a distance which is hydrodynamic radius of one of these things. So this, I just want to emphasize that this is very similar to Debye screening lens in electrostatics, except lens is different, but the structure is very similar, and this is not a coincidence. There is deep analogy there. Yes?
So this is true for obstacles that are considered to be immobile, right?
Yes.
But if the obstacles can move, then this doesn't hold anymore, right?
Well, it then depends on how they move, and then you have to consider jointly movement of your solvent and movement of your particles and see what happens. Of course, if all particles can move and maybe they move together with the flow, then it's a different story. So this is hydrodynamic screening. And this hydrodynamic screening means that in the context of a polymer, it means that if these two forces somehow act on the system, their effect cannot propagate infinitely far. It can propagate only into the polymeric system only over a certain distance. This is number one. Okay, number two, the idea that this force dipole acts simultaneously on two things. So if you look at it, the problem from the symmetry point of view, then all possible force dipoles can be classified into three classes, three categories, here indicated by these pictures. So in one case, both forces are exerted on the polymer, like this one. Exactly like this one, both forces exerted on the polymer. Here, both forces from the back pose and forward pose exerted on the solvent. It's just a swimmer. And this is not interesting, not particularly interesting in context of chromatin. You can, of course, imagine that there is some swimmer, some, I don't know, bacteria or somebody who decides to swim inside chromatin. But this is more serious thinking than anything else. And this is finally the interesting type of force dipole, where one force is exerted on the polymer here, and another force is exerted on the solvent. So symmetry-wise, this object is a director. A director, or I think there is some other word for it. It's apolar vector or something like that. So it's vector with two arrows in both directions. So it's symmetric, although polar bear is not quite symmetric, but force-wise it is symmetric. While this thing, in terms of symmetry, it's vector. It's like ferromagnetic. It's very different symmetry. So this, for a theorist like myself, this smells very well. It smells some theory-based classification. And so basically our theory was based on this assumption. And now we face the necessity to develop another theory for this one. How do we do that? Okay, so we should remember that apart from active contribution to the stress, which we discussed, and active contribution to osmotic pressure, which we discussed, there is a possibility of this thing. And this thing means that you have active force exerted on the polymer and the same force with opposite sign exerted on the solvent. This is force dipole of a new kind, and this piece is Doi and Anouki equation, and this pink addition is something that Doi and Anouki did not consider because they didn't need it. But we add this thing. So how do we write it? We say that, okay, if there is some density of motor rho of these motors per unit volume, and F is the force exerted by every motor, and M is the vector which shows the direction of this force. Okay, so then this is the same thing with the opposite sign, and we have now mathematical problem. Okay, so first of all, we can consider what happens in the simplest possible case. In the simplest case, when we assume that the system overall is incompressible. So there is only transverse modes, incompressible system. Overall, density variations of chromatin are irrelevant. We do not consider them. It's not, by the way, it's not necessarily true. Of course, it's not true. We discussed that heterochromatin and euchromatin have different densities, but for mathematical treatment, let's first consider that this density is fixed. Okay, so then the only thing that exists is basically the relative velocity of polymer with respect to the solvent. How solvent is pushed? And this is exactly your question. How solvent moves past polymer, how they move with respect to one another. This is this W. So if you go through this mathematics, you discover this equation, which is painfully familiar to everyone who studied Debye screening in electrostatics. It is the same equation. This describes the screening. And this is the screening length, and this screening length is proportional to concentration of monomers to the power minus 1/2, as my estimate suggested. So this is all consistent, but the thing that is screened is relative motion of polymer and solvent. And now here, in the Debye theory, here would be charge, some source of electric field, some charge. What plays the role of source for this relative motion? This is, of course, density of these motors times the force of every motor divided by solvent viscosity and multiplied by average orientation of these sources. So importantly, this relative velocity is now driven by force monopoles. It's not force dipoles. It's driven by force monopoles because it's relative velocity. Initially, there was force dipoles, of course. One leg of the dipole, another leg of the dipole, opposite signs, some is zero. But for relative velocity, it's driven by force monopoles. Because when you have this motor that acts like one force on the polymer and another force on the solvent, what it does is exactly it pushes solvent with respect to the polymer. It is force monopole. And of course, force monopoles are much stronger than force dipoles. They, of course, generate much bigger effect. Indeed, what happens? Well, I have to tell you the other part of the story, how this average orientation of these dipoles, how does it evolve? Well, if my force dipole if my motor is attached to the polymer in this place, it can still swiggle. It can rotate like this around the attachment point. And if there is a flow of solvent past this, indicated by arrows, this flow, of course, exerts a torque on the motor and prefers, and by the way, at this point, I, of course, should tell you that who is this motor? It's most likely RNA polymerase. So if there is nascent RNA being produced, there is a tail, and if there is this relative flow, then it exerts some torque and reorient them, and therefore this vector M evolves like this. This is just entropy-driven reorientation, and this is this torque. Okay, so if you go through this mathematics now, it's very simple. What you obtain is you obtain basically you can say you obtain this phase diagram where this is spatial scale and this is force. And if force, applied force of every monomer exceeds a certain threshold, which is indicated here, which corresponds to velocity generated by fully ordered motors, which is characterized by the strength of these motors, divided by velocity needed to order motors against entropic reorientation. If this exceeds 1, then you obtain this desirable nematic order. Then these motors form nematic order. Thanks God, they form nematic order, and then, of course, they form domains and everything else. Because they work cooperatively. These motors now help each other. They speak to each other, because each of them is force monopole for relative motion. And because each of them feels the flow, they undergo, if the force exceeds critical value, they undergo phase transition, which is non-equilibrium phase transition, and which is nevertheless similar to the phase transition of, let's say, paramagnetic to ferromagnetic, because they are now ordered. They are ordered, and if the force becomes bigger than critical, they form order, and then this order becomes the domain of coherent flow. So this basically shows here in mathematical form. So here is a little better drawing. In the simplest case, which we were able to analyze numerically in complete details, when the domain, I call it nucleus or cell nucleus of a spherical cow. Spherical cow, of course, has a nucleus in the form of a sphere, and inside the sphere there is this sort of a washing machine type flow. The solvent flows this way, and the polymer, by the way, of course, flows much, much more slowly than the solvent, because polymer is more viscous. So mostly solvent goes like this, or in three-dimensional drawing, it goes like this, and this is similar to how children play, like this. Okay, this is still the same criteria. And of course, depending on the size of this domain, the amount of force that you need increases if you have small domain. So let me see how I'm doing in terms of time. I better skip. There are some interesting details here but I will go quickly through this. So this solution, this beautiful washing machine solution, was based on the idea that density of polymer does not change. How about if density of polymer does change? If density of polymer does change, then of course we can obtain different types of motion, and in particular we can obtain something that it looks like sustained oscillations or waves, which are sustained despite the friction that exists there because there is constant ATP activity. So how does it look like mathematically? What happens is you now have, for your relative velocity between polymer and solvent, you have now this equation, which is a little bit cumbersome equation, but if you carefully look at it, you discovered something familiar. This is simply equation for harmonic oscillator. This is mass times acceleration. Acceleration is the second derivative in time, so this is mass, okay? So this is the restoring force, spring constant times velocity. And this is friction. And the friction involves this active process, force of motors, density of motors, and so on. So this is friction, okay? So if force becomes large, then friction becomes negative. Effective friction becomes negative, and that means the system becomes unstable, and you have this oscillation. So what is the nature of oscillations? Here is my explanation of these oscillations, and this is actually a poor man's movie. I wanted my student to generate a real movie, to pretend to be a real professional, but instead he graduated, defended his PhD, and now he is doing something else, so he doesn't want to do the movie. So this is poor man's movie. So imagine that, and maybe it's better than a real movie. So imagine that at the beginning, for some reason, there is fluctuation of polymer density. Polymer, for some reason, I'm exaggerating dramatically. Polymer, for some reason, occupies only 1/2 of the volume very densely, and another half of the volume is empty. Pure solvent. Okay, so because of diffusion, polymer now moves this way, expands into the place where concentration of polymer is low, while solvent, of course, moves the opposite direction to balance the total density. When solvent moves this way and polymer moves this way, there is a relative motion. One moves past the other. And this exerts the torques on all the motors that are there. So while they are moving like this, they help motors to orient in this direction. They help these motors to orient like this, and by the time polymer is happily uniformly distributed in space in terms of density, these motors are now very much oriented, and they work like crazy. They pump solvent in that direction and pump polymer, push polymer in that direction. So as a result, because of the action of the motor, they now lead to polymer concentrating on this half and solvent on that half, and the process repeats itself. So as long as these motors work, there is this type of instability. So in the end of the day, there is this phase diagram depending on the size of domain, depending on the size of the nucleus. If force is very small or the number of motors is small, then you don't have anything interesting. In this intermediate case, you have this washing machine type behavior in which polymer density does not change, and in even bigger force, you have this sustained oscillation. Okay, so all of this was, yes, please.
How does this depend on the volume ratio between the polymer and the solvent?
Well, it is everywhere there. Okay, so this volume ratio is this phi naught. And so this length scale lambda d is very much dependent. Phi naught is average volume fraction of the polymer. Average volume fraction of the polymer.
Is there that much solvent in the nucleus?
Sorry?
Is there that much solvent in the nucleus compared to the volume occupied by the polymer?
Well, we discussed that, in fact, and rough estimate, it depends a little bit of what you consider to be, where you draw the boundary, what is polymer and what is not polymer. So depending on that, fraction of the solvent is 70%, 80%, 60%, 90% on that level. There is a lot of polymer in the sense that density of polymer is much larger than what Dejean called C star. Density of polymer is larger than C star, and therefore this polymer is either a globule, if you think about it in terms of Lifshitz globules, or semi-dilute solution, if you prefer Dejean's terminology about solutions. It's something of this sort. It's C greater than C star. But there is a lot of solvent, yes. It's not dry at all. Yes?
I can ask a question about something you said before. There are two types of dipoles. There are pushing dipoles and pullers. So you explained that with pushers you get that. Why don't you get any strong effect with pushers?
It's super interesting, yes.
Both theories of active systems, there is a difference between pushers and pullers, but there's always some instabilities coming on.
Okay, so these guys, as you see, they described the difference between extensile and contractile motors, which are the same as pushers. Yes, absolutely. And if you read the title of the paper, Coherent Motion Model, I thought it's even in the title anyway, but they emphasize that only pushers have this effect, not pullers. Only pushers. So this is equally well reproduced in our model. So for our model, pusher would be this little f greater than 0, and if f is less than 0, then this is a puller. So you see that this f, this quantity must exceed 1, and therefore it exists only if f is positive. And if f is negative,
I understand. Can I ask you a question? Sorry, a related question is your little bar magnet things, one end of which attaches to the polymer, and the other end of which exerts a force on the fluid, sort of like the way a flagella, a bacterial flagella does. You can imagine inventing a protein which could do this. Are you saying that this is a protein whose existence we know?
most likely.
Are you saying there must be such a protein and we should go and look for it? I'm confused about this. What's the actual realization of this?
I think that the most plausible candidate for for the role of this motor is RNA polymerase.
Well, it has to have something that can push on the fluid, which means it has to be something like
It is sufficient.
a motor, and
Well,
and grab onto the polymer on the other. Both are understandable. You could invent a protein that does this, I would imagine. But I'd like to know a little bit more about its, actual realization in the world we live in.
I would like to know more than I do about it too, which means I don't know too much about it, but I want to say that RNA polymerase, as we understand it now, as I understand it now, is already good enough to exert such pair of forces, because what it does is it walks along polymer and therefore definitely exerts force on the polymer. That's for sure.
Harder it is to effectively push on the fluid.
Well, whether it effectively pushes on the fluid or not, I do not know. It depends on how you want to define effectiveness. But the fact that it pushes on the fluid is undoubtedly true in my mind, because otherwise it's unclear where the counter force otherwise can go. If it exerts a force on the polymer, it must exert force on something else.
Your view is that, or your idea is that these are RNA polymerases that are not currently engaged in making messenger RNA, let's say, but are hanging about and they're doing something else possibly useful, namely swirling.
Maybe like this, or maybe they do it while they synthesize this mRNA. I see no reason why they cannot do it at the same time.
People do all kinds of experiments with individual RNA polymerases.
Yes, indeed, and indeed they measure the force, and this force is about on the polymer, yes. And if the force is exerted on the polymer, then, as I said, Archimedes told us that some compensating force must be exerted on something else.
What people measure in single molecule experiments is the stored force of the RNA polymerase. Right. How much you should pull it back and stop it. The total force in the molecule itself should be zero. Right.
Exactly, yeah. So if you... That's why I think that if you do not, you see, if you want to know how much force, let's say, Peugeot car exerts, you hold it by back bumper and you measure how much force it generates, and then it doesn't move anywhere. But when it does move somewhere, then it has to push on something else. And in this case, I see no place other than the solvent, which is difficult to see, I agree, but
So what would be the counter force for you? The solvent force is extremely small if you calculate it. Hydrodynamic friction is about zero.
why is it about zero? It's
Just assume, look at the size of the
yeah.
rays you stoke slow and you find something extremely small.
No, the polymerase has the RNA hanging, which is full of
So if
iterative
you put the RNA somehow or something like this,
Yeah.
it would work, I agree.
That's what I'm thinking, and I have some subsequent slides in which I made some numerical estimates that seemed to work. I don't know. Maybe they are not, but okay. So back to the question of pusher and puller. Yes, only pushers generate this type of instability, and pullers do not.
So do you have any, I mean, I understand the math, there's no problem. Do you have a qualitative argument of why pushers do something and pullers don't do anything?
It seems when you look at this picture, it seems sort of obvious that when you have pushers, then they generate this type of the flow, and this type of the flow speaks between them. When you have pullers, they do not speak to one another. It's not a very good explanation, but somehow it always felt so intuitive to me that I did not think how to explain it better.
Another thing which is important in classical theories of active matter is flow alignment. How the flows that you create realign your...
That's exactly what is happening here. That is exactly what I'm talking about. Yes, this is this picture. This is how the flow that this flow indicated by the arrows is generated presumably by all other motors around, and this flow. Here is possibly a good explanation for your other question, Jean-François. So if other motors generate flow like this, they help this guy to turn with its blue end down. Okay, so and if it is pusher, then it contributes constructively to the same flow. It pushes flow in the same direction that flow already exists. If it, on the other hand, if it is a puller, it will turn the same way, but it will push, rather pull, the flow in opposite directions. So it will dampen the flow rather than support the flow. So instead of positive feedback, there will be negative feedback. That is a little more intuitive, I think.
Yes.
Okay, so all of this was linear instability. We analyzed what happens in a nonlinear case. I call this simple and nice monstrous equation, but it's monstrous and I don't want to go there. Enough it would be to say that nonlinearity arrests the growth of these instabilities, and so that's all. So one thing that might be useful to say in conclusion, and I think I should stop at this point, so I will just say this and stop. In some way, this nematic that is generated by this hydrodynamic interaction and which I hypothesize is behind these domains observed by Alexandra Zydowska, is similar to active nematic, which active nematics are studied to death by many people, starting from Zvonimir-Dodgik experiment. So there are two differences between our case and this active nematic case. The first, a little formal, is that ours is not nematic, but rather ferromagnetic or ferroelectric, because of symmetry. These motors have arrows. They orient. If they are RNA polymerase, they push RNA polymerase in one direction, which is different. And more importantly, active nematic usually are materials which are nematic because they want to be nematic, because they consist of elongated filaments. And then there are some molecular motors or some activity or something. They become active nematics. Ours are not nematics on their own. or ferromagnetics, they are ordered only because of activity. So that is, I think, fundamental difference. Okay, so I will have to stop at this point, so I skip these numbers. I will end up showing the collection, a potpourri of pictures that I showed during my lectures here. I chose some pictures, and I also want to leave you with this quotation from James Maxwell. Maxwell, it turns out, was a big friend of Tate. They were schoolmates. They were learning school together, and they kept exchanging letters all their lives. To save on stamps, they were sending postcards, and these postcards exist somewhere. And frequently, Maxwell would write postcards in poetry. So once he wrote this paraphrase of Shelley. In Shelley, it was, "My soul is an enchanted boat." And Maxwell wrote, "My soul is an entangled knot." And Maxwell was quite a man. And in particular, the last line of this, "All the tools for its untying in four-dimensional space are lying." It is true that knots do not exist in 4 dimensions. But the fact that Maxwell rhymed it in 9th century, it drives me nuts. I think it's something. So I want to leave you with this little interesting observation. So thank you very much for the attention. And sorry I was too long.